Hello, my name is Alex Kavanaugh, and this presentation will be on the effects of Mach tuck. First, we'll talk about what is Mach tuck. Mach tuck is an aerodynamic effect that shifts the center of pressure towards the trailing edge of a wing. And what this ends up doing is inducing a nose-down pitching moment on an aircraft. If we take a look at the two drawings on the right, looking at the top right drawing, we see that there is an incoming free stream velocity that's sufficient to cause a normal shock to occur on the surface of the wing. And if we look before the normal shock, we see an area of high lift due to the increased velocity, and we see a larger area of less lift due to the decreased velocity. If we were to increase the free stream velocity, such as in this second picture, we wind up shifting the normal shock towards the trailing edge of the wing. And this creates a larger area of high lift before the normal shock, and then the size of the low lift area is reduced. And what this does is it moves back the location of the center of pressure. And ultimately, this larger lift plus a larger lever arm winds up inducing a larger moment about the center of gravity of an aircraft. And this is a nose down pitching moment. So we can see that this is felt more drastically with increasing speed. And it's also highly dependent on the shape of the airfoil, which is what we're going to explore in this presentation. And this can be very difficult to mitigate with control surfaces alone. One of the first times that we encountered Mach tuck was when we were producing the Lockheed P-38 Lightning. This was one of the first aircraft that could go faster than 400 miles per hour, and because of this, it felt the effects of Mach tuck very strongly. Once Mach tuck started, the aircraft became extremely stable in this configuration, and it was difficult to have enough control authority to leave this cycle of increasing airspeed, which increases Mach tuck, which increases the airspeed more, which increases the effect of Mach tuck more, and so on. And so we knew that we needed to find some way to mitigate the effects of Mach tuck. So the purpose of this project was to explore the various effects of Mach tuck on various airfoils at transonic speeds, as well as to characterize the types of different airfoils to use on transonic aircraft. And the way that this was explored was using a program called TS-Foil that was developed at NASA. And what this program does is solves the transonic small disturbance theory equations. The airfoils selected for this research were the SC2-0610, a biconvex 2% airfoil, the NACA 0012 airfoil, as well as the NACA 23015. And the reason that these airfoils were selected is because they're pretty different from one another. The SC2, the supercritical airfoil, is more found in transonic applications, while the biconvex airfoil is more found in supersonic applications, and the NACA airfoils are generally found in more subsonic applications. So we wanted to choose these different airfoils to see what features cause desirable flow characteristics in transonic flows. The results of simulating these airfoils in transonic conditions using TS-Foil are shown here. The first point is that most airfoils converge to a center of pressure location at about half the chord length. And this isn't very surprising. This is what we would expect. But next, it's important to notice that the NACA airfoils see a very large change in the location of the center of pressure, whereas the supercritical airfoil sees only a small change in the center of pressure location when we change our Mach number. This is a lot more desirable as we don't want small perturbations in our Mach number to cause large perturbations in the location of the center of pressure on our wings, because these large changes in the center of pressure location are going to drastically change the moment that's applied on the aircraft. The last thing to notice is that the biconvex airfoil only goes up to about Mach 0.75. This is because we saw some unsteady flow characteristics moving past Mach 0.75, and so we can say pretty much right off the bat that the biconvex airfoil would not be a good candidate for transonic flow applications. Now, if we take a look at a typical subsonic airfoil, such as the NACA 0012, and we put it into a free stream velocity of Mach 0.5, we can see that there's no shock on the surface of the wing, and we see this relatively smooth gradient on the upper and lower surfaces of the wing. Additionally, the pressure coefficient distribution across the chord is pretty smooth. There's no large discontinuities or anything like that. However, if we were to increase the free stream velocity to Mach 0.75, we do wind up getting a shock at about half of the chord length on the wing. Now this is a big problem because when we have this shock, we wind up having a large discontinuity in the lift characteristics of the wing depending on where we are in the chord. And when this discontinuity can move around a lot on the surface of the wing, we wind up getting large changes in the moment that's applied about the CG of the aircraft. So ideally, we would like this shock to just occur in one location, if it has to occur at all, so that way we have a constant moment applied about the CG of the aircraft. Looking at the results for the supercritical airfoil, first at a free stream Mach number of 0.5, we can see that we have a very sharp deceleration in the flow just after the leading edge of the airfoil. If we were to increase the free stream Mach number to 0.75, we can see that instead of this deceleration happening at the leading edge, it actually gets pushed all the way to the trailing edge of the airfoil. And really, this is an ideal scenario for a transonic airfoil or a transonic wing, because we want the center of pressure to not move around a lot, and having a small shock at the leading edge versus having a small shock at the trailing edge of the airfoil is going to produce very similar results in terms of the location of the center of pressure, because we don't have this large discontinuity in the lift characteristics of the wing or airfoil moving around on the surface, which is what essentially causes the large changes in the pitching moment applied on the aircraft. Some conclusions from this research were that supercritical airfoils drastically outperform subsonic airfoils and most likely would outperform supersonic airfoils as well in transonic flows, which of course isn't surprising. This is one of the main reasons that supercritical airfoils were invented, were for use in transonic flows. But transonic aircraft also benefit from the use of supercritical airfoils due to decreased drag, since we're moving the shock wave to the trailing edge of the wing, an increased drag divergence number. Structurally, we can have a more efficient wing design with a thicker leading edge. We can also reduce the shock-induced boundary layer separation. Now, we could also implement control surfaces to mitigate Mach tuck, but this wouldn't be nearly as effective since we're going to have increased drag, and it would also be a lot more difficult to control, similar to the problem that the P-38 Lightning had, where it becomes very difficult to exit this configuration. As I had mentioned earlier, the biconvex airfoil exhibited unsteady flow characteristics once we moved past a free stream Mach number of 0.75, and this made them more difficult to analyze, but it's likely that these unsteady flow conditions would cause large changes in the pitching moment of the aircraft, and this is undesirable for transonic flight. This matches what we would see in industry, where we find biconvex airfoils more in supersonic flow applications. So the main takeaway of this research is that using a wing with a large radius of curvature leading edge and a sharply concave bottom side trailing edge yields the most efficiency in transonic flight, while also providing the best mitigation of Mach tuck. Thank you.